Good afternoon. If we recall, we were we have introduced reaction turbine, and then we have I have told that in reaction turbine there will be rows of fixed blade and moving blade one after another. That means one row of moving blade, then one row of fixed blade, then one row of moving blade, like this. And I have told that in case of reaction turbine, we will have pressure drop both in the moving blade rows and in the fixed blade rows. Earlier, in case of impulse turbine, we have got pressure drop only in the nozzle, which is equivalent to fixed blade, but here we will have pressure drop both in the moving blade rows and in the fixed blade rows. So, that is the main difference between the reaction turbine and the impulse turbine. And then we define some sort of degree of reaction. Again, I like to start from that point. So, degree of reaction, and this is defined as R. So, R we will call as delta H MB. MB is the subscript used for moving blade, divided by total enthalpy drop that comes from delta H moving blade plus delta H fixed blade. Now, this is for a particular stage. So, in a stage there will be one row of moving blade and one row of fixed blade. So, basically it is for a particular stage we are defining degree of reaction. And in our last class, if you remember, we have drawn a schematic diagram of these two rows of blades, that means row of moving blade and row of fixed blade. And then I have also shown how the pressure is changing from one row to another or in between a row, and how the velocity is changing, how the velocity is varying with different rows of blades. And then I have told probably that basically the nozzles, they also look like blades, and we use same type of configuration or construction for making the moving blade and making the fixed blade or making the nozzle. So, due to the ease of manufacturing, due to the ease of fabrication and of course inventory, etc. So, we do not differentiate between the moving blades and the fixed blades. They are made of same geometry. If we make of same geometry, then it is expected that same amount of enthalpy drop will take place in the moving blade and in the fixed blade. If that is so, then we can write if the geometry of moving and fixed blades are identical, then we get delta H MB is equal to delta H fixed blade FB, R is equal to 0.5 or degree of reaction is 50%. So, this is a very commonly used design feature, that the blades are of same design and we have got reaction turbine with a degree of reaction equal to 50% or 0.5. With this, we can go for now the velocity triangle. We can now have a construction of velocity triangle. So, if we write velocity triangle for reaction turbine, and we can write R is equal to 0.5, then we will have the velocity triangle like this. Let us use another color for something like this. So, we can show the different direction of different velocities. This is, we know from our earlier knowledge, this is VR1, that is the relative velocity at the inlet of the blade. Then this is V1, absolute velocity at the inlet of the blade. Then this is your VR2, relative velocity at the blade exit. Then this is V2, that is absolute velocity at the blade exit, and this one is VB, that is tangential velocity of the blade due to the rotation of the turbine. Then we can define different angles just like before. So, we have got beta 1, which is the blade inlet angle, and here again, as I have told number of times earlier, the design is such that the steam enters smoothly without any shock or collision into the blade. It glides into the blade. Okay. This is beta 1, and then this angle we call alpha. This angle is beta 2, and if you remember, we have defined this angle as delta. Now, I am not drawing the generalized velocity diagram for a reaction turbine. I am drawing the velocity diagram for a special case when R is equal to 0.5. Okay. That means, there is equal enthalpy drop in the row of fixed blade and in the row of moving blade. If we do that, then we will get a very interesting relationship. We will get V1 is equal to VR2 and VR1 is equal to V2. This relationship we will get. So, we have to remember that this is a relationship which we do not get for all the reaction turbine, but this is the relationship we get for the special case when degree of reaction is 0.5. All right. Similarly, we will get another relationship. That relationship is also equally important, that is alpha is equal to beta 2. So, this relationship we will get. Now, you can see the difference between your impulse turbine and reaction turbine. In case of impulse turbine, I have told generally symmetric blades are used. What does it mean? That beta 1 is equal to beta 2. Okay. In most of the design, we will have beta 1 is equal to beta 2, but here beta 1 need not be equal to beta 2, but alpha that will be equal to beta 2. The reason is quite obvious, because from one row of blade the steam has to come out and it has to enter the next row of blade smoothly. Okay. So, that is why this type of relationship we will get, and of course, we can see this diagram. From this diagram also we will get this type of a relationship. And then we can get another relationship, that is beta 1. What is beta 1? Beta 1 we will get as 180 degree minus delta. This relationship also you will get. See, this angle and this angle, they are same. Maybe my diagram is not that good, but these two angles are same. This angle and this angle are same. So, from there we will get beta 1 is equal to 180 degree minus delta. So, these are the relationship we will get for angle and the different velocity components. All right. Now, actually some people also like to show that this VR2, there is some contribution from the impulse point of view and some contribution from the reaction point of view. So, generally some people wants to show that this is made up of two parts and maybe this is a contribution from the reaction of the turbine. All right. And then just like previous analysis, what we can do, we can determine what is del V omega, whirl component of velocity. Keeping this diagram in mind, one can write del V omega, that is equal to V1 cos of alpha minus V2 cos of delta. Just let us see what is del V omega. Del V omega is this quantity. So, del V omega I have shown here, and that is V1 cos of alpha minus V2 cos of delta, and from there we can get basically V1 cos of alpha plus VR2 cos of beta 2 minus VB. Okay. Then we can use the relationship between V1 and VR2, and we can ultimately write twice V1 cos of alpha minus VB. This we can write. Then work done, we can write WD. This subscript D comes from diagram. From the diagram we are determining all this different component of velocity, different component of force, etc. So, that is delta VW into VB, that is equal to twice V1, sorry, this 2 is inside, twice V1 cos of alpha minus VB multiplied by VB. Remember, or please note down that this particular expression is for unit mass flow rate of steam. If we multiply it with omega s, which we have used earlier, that will give you the total amount of work done. This is work done per unit mass flow of steam. All right. So, this is work done per kg of steam flow. Similarly, we can determine what is the energy input to the blades per kg of steam. So, we can write energy input to the blades per kg of steam. So, what is this quantity? Now, one has to be bit careful here. Initially, steam is entering the blade passage with a velocity v1. So, that kinetic energy will be there. So, per kg steam, that kinetic energy will be v1 square by 2. Then in the blade, in the moving blade, there will be increase of velocity because there is expansion of steam. Blade passage is such that there is a pressure drop. So, we will have increase of steam velocity. Which velocity increase we will get? Let us say there is no increase of steam velocity. Then what happens? Whatever is the relative velocity at the entry, we will have same relative velocity at the exit. Okay. But here the blade passage is such that some amount of velocity increase is there as there is expansion. So, we will have also increase in kinetic energy while the steam flows through the blade passage. So, basically we will have v1 square by 2, this is same as it was in impulse blading, plus we will have Vr2 square minus Vr1 square divided by 2. So, this we will have. Now, if we remember that Vr2 is equal to V1 for 50% reaction. So, we can have from here V1 square minus Vr1 square by 2. That is the energy input to the blade. And again, if we utilize the geometry, then we can get energy input is equal to V1 square minus Vb square minus twice Vb cos of alpha divided by 2. So, if we use the geometry of the velocity triangle and the relationship which I have given for 50% reaction, if we use this, then we will get this relationship. Why we are doing this exercise? Because we want to have, instead of number of different velocity components, we want to express all the relationships in terms of V1 and Vb. V1 is the input velocity to the blade passage and Vb is the velocity in the tangential direction. So, these two we want to have in all our expression, and also we want to have one angle, that is the inlet nozzle angle or nozzle angle. So, that is alpha. So, that is why replacing all the other velocity component, I have given the expression in terms of V1, Vb, alpha, etc. Now, with this, what one can do? One can define the stage efficiency or diagram efficiency of the blades. Diagram efficiency of the blade. So, it is defined just like before, that means what is the work we are deriving from the blade and the energy in terms of kinetic energy, that is input to the blade. And whatever we have done, if we write that, so we will have eta d, that is equal to twice V1 cos of alpha minus Vb multiplied by Vb, this divided by V1 square minus Vb square minus twice V1 Vb cos of alpha, and I think this divided by 2. So, at the top there will be 1 2 term will, I mean this 2 that will come here. So, now we have got the diagram efficiency in terms of V1, Vb and alpha. Then just like before, we can introduce one particular parameter, that is rho. Rho is the velocity ratio and we define it as Vb by V1. Once we introduce that, so we will get a complex expression in terms of rho and in terms of alpha. So, that expression one can get, that means I can write that eta d now will be a function of rho and alpha, that means rho and cos of alpha. So, from here one can get, just like our previous exercise, one can get the expression for rho for the maximum efficiency. That means, one can do this exercise d rho d by d eta d by d rho, that is equal to 0 for maximum efficiency, that one can write, and then this will give you rho optimal is equal to cos of alpha. So, this is the value of optimum velocity ratio we will get, and then Vb is equal to V1 cos of alpha, not for all the cases, for 50% reaction turbine and when we are looking for maximum efficiency. So, if we, so Vb will be V1 cos of alpha. Does it give you some sort of hints? What will be the shape of the velocity triangle? Yeah. So, then V1 cos alpha means, so V1 has to, V1 cos alpha means this VR1 has to be at 90 degree with Vb. Okay. Then VR1 has to be at 90 degree with Vb. Okay. So, we will have eta d diagram efficiency maximum is equal to twice cos square alpha divided by 1 plus cos square alpha. So, this will be the efficiency of a particular stage, of course, for the 50% reaction turbine and when our efficiency is maximum. This is the maximum value of efficiency what one can get. And if we draw the diagram, we will get something like this. So, this angle is your beta, what it is, beta 2, and this angle is alpha, this is VR2, this is V1, this is VR1, this is V2, and this angle will be your beta 1, all right, and this quantity is nothing but delta VW, wall component of velocity. So, this is what we will get in case of let me write it, velocity diagram for 50% reaction turbine and operating with maximum efficiency. So, this will be the representation of the velocity diagram. Now, we will have equal enthalpy drop in all the stages. So, that is why design of a reaction turbine that is that is guided by this particular principle. If it is 50% reaction turbine, and most of the cases it is 50% reaction turbine, that we can decide upon the number of stages by fixing what will be the enthalpy drop in a particular stage. Okay. So, that we can decide upon, and then accordingly we apportion the amount of enthalpy drop for each of these stages. So, basically we do not differentiate between the nozzle and blade. So, we have got rows of blade, alternate rows of blade, we call them moving rows of moving blade and rows of fixed blade. Some other name also is given because the moving blades are mounted over the rotor, they are called rotor blades, and the fixed blade they are mounted on the casing. So, they are sometimes called stator blade. So, we will have alternate rows of rotor blades and stator blades, and in each of the blade row there will be delta H amount of enthalpy drop. Now, I think let us have some sort of a comparison when we have made these studies of impulse turbine and reaction turbine. Now, if we see, we will see if we do some analysis, we have seen basically three types of arrangement, and this is the basic arrangement for any turbine. So, in one arrangement, let me call it basic impulse stage. So, what is a basic impulse stage? See, basic impulse stage is like this. We have got one row of nozzle and one row of moving blade. So, one row of nozzle and one row of moving blade. Well, one can call this basic impulse stage also as a pressure stage, means this is, if we repeat this time and again, then we will have pressure compounding or rotate compounding of the impulse turbine. One row of nozzle, there pressure drop will take place, velocity will increase, and then it will go to the impulse moving impulse blading. So, there will be decrease in velocity. Okay. Again it will go to one row of nozzle and its pressure will decrease, velocity will increase. So, this can be called as basic impulse stage, or one can look this stage as a rot stage. This is one. Then one can have two rows of Carty stage. So, here you will have one row of fixed blade, one row of moving blade, one row of fixed blade, one row of moving blade, like this. Okay. So, this is another arrangement. Then third, you can have that reaction stage, that means one row of fixed blade plus one row of moving blade, within bracket let me write, with pressure drop in both the rows. Okay. So, these are the three basic arrangement what one can get. Now, if we make a comparison, then we will see that output, let us say output we call it P. Okay. Let us denote output by P. So, we will have P 2 row of Carty stage, that will be greater than P basic impulse stage, that will be greater than P, that is reaction stage. So, if we see the output for similar conditions, then we will have largest output in a Carty stage, then we will have some intermediate output in the basic impulse stage, and then we will have the lowest or the minimum output in the reaction stage. Whereas, if we consider the efficiency, okay, let us have a comparison of efficiency. Now, if we have efficiency in this direction, can you tell me what is the maximum efficiency we have got? Let us say this is rho. In this direction we have got rho. In the basic impulse stage, what is the maximum efficiency we have got? Can you tell me? That was less than cos square alpha. If you see, it was less than cos square alpha. So, this efficiency was less than cos square alpha. Okay. And that value was, so we have got two stages of Carty's. So, the value of rho was cos alpha by 4, if you remember. If you remember, that value was cos alpha by 4, rho value was cos alpha by 4. So, let me write cos of alpha by 4. Then, if you have considered the basic impulse stage or the rot stage, this was efficiency was cos square alpha, and this was cos of alpha divided by 2. This we have derived earlier. And then just now we have derived for reaction stage. So, for reaction stage, what did we derive? This was rho was cos of alpha and the efficiency was 2 cos square alpha by 1 plus cos square alpha. So, obviously, this will be higher compared to the previous values because cos alpha has got a value lower than, it has a value less than 1. So, this is the efficiency curve for different arrangement of turbine, steam turbine. So, let me write, let us say this is Vc, velocity compounding, let us say this is Pc, pressure compounding, and let us say this is R, reaction turbine. All right. Now, let us go back to our earlier diagram or earlier discussion. So, if we see, if we compared output, then we have got P2RC, means 2 stages of Curtis, that is better than, output wise it is more than 1 basic impulse stage, and again the basic impulse stage is better than the reaction stage. What does it mean? That with 2 stage of Curtis, whatever output we can get, we need much more stages of reaction turbine if we have to get same output. Okay. So, what does it mean? That means more rows of blade will be there if we go for only reaction stage, whereas with less number of blades we can have same output if we have got velocity compounding impulse turbine in the impulse turbine. Similarly, we can write the other information just now we have got, that is reaction stage, that will be greater than efficiency of basic impulse turbine or pressure stage, that will be greater than the efficiency of velocity compounding or Curtis stage. Okay. So, you see that these two informations are opposite to each other. So, that is why in a steam turbine design, particularly if it is a large steam turbine, then we should have combination of all the 3 stages to have the maximum benefit out of the supplied steam. Okay. And it is like this. To start with, we will have Curtis stage or velocity compounding, then we can have this pressure compounding, and then for the last stages we can have the reaction stage. Okay. So, that is what is done in case of steam turbine. That is how the different stages are allocated in a particular turbine. So, this almost brings us at the end of our discussion. We do not have much time to discuss other aspects of steam turbine. So, I have given the basic outline, how does it work and mathematical equations, etc. But what I like to discuss more, that there are certain losses which I like to discuss. What are the different type of losses which will occur in a steam turbine? So, different losses which we will come across in a steam turbine are like this. Losses in a steam turbine. Loss in the regulating valve, then we will have loss in the nozzle, I will explain. Then blade friction loss, then we will have disc friction loss, then we will have partial admission loss, then we will have gland loss, then we can have residual velocity loss, and then we can have carryover loss. So, one by one let us discuss the different losses. Loss in the regulating valve, that is from the boiler the steam will be supplied to the turbine and there will be some sort of a regulating valve, and we know regulating valve or any valve for that matter is a throttling device. Okay. And in the throttling device we will have loss in pressure, there will be a pressure drop, okay. And due to that some amount of, obviously why pressure drop is taking place, the steam has to flow through a narrow passage, and that is why there will be certain amount of loss. Then loss in the nozzle, though nozzle is a small component, its length is not large, it is not a very long passage, but even then the steam has to pass, and when the steam is coming out of the nozzle then it will have sufficient amount of velocity. So, one thing, when it is passing through the passage of the nozzle there will be frictional loss and there could be certain amount of heat loss also. Then blade friction loss, this is also the same type of thing, that means when the steam is passing through the blade passage then there will be friction and we will have certain amount of loss in energy. Disc friction loss, see the turbine it is, as we have seen, that we have to maintain certain ratio between V1 and VB. Okay. We have seen for the optimum operation of the turbine we have to maintain certain ratio between VB and V1, that is inlet velocity and the tangential velocity. And what is the tangential velocity? Tangential velocity is again a function of RPM and diameter. Diameter is the mean diameter of the blade, mean diameter of the blade. Now, mean diameter of the blade cannot be made very long. So, they are mounted over some disc or drum. So, that is also rotating in a passage which is filled up with steam. So, there will be some amount of churning action and we will have certain amount of loss. Then comes partial admission loss. This we have to understand and we have to visualize the phenomenon inside the steam turbine. It is like this: the blades are mounted over the periphery of the rotor, drum or disc, and there are large number of blades, small blades, and they are uniformly located over the rotor, drum or disc. Now, the steam should enter and approach all the blades. So, there are nozzles or slots. Now, generally these nozzles and slots, they are not throughout the periphery just before the entrance of the blade, entrance to the blade. So, there are slots, part of the periphery and part of the peripheral passage is blocked. So, due to that you will have steam flow through the slotted portion only, and where there is no slot, there obviously will not be any steam flow. This induces certain amount of loss, and this is known as partial admission loss. Then gland loss. Actually, if we see that there is a casing, let us say this is the casing. I am drawing a very rough sketch and very schematic representation. This is the casing, and you will have, this is the shaft. This is the shaft on which turbine blades are mounted. So, this is a rotating component. These blades are mounted on this, and this is a rotating component, and this is a fixed component. So, obviously, this cannot be securely fixed on the moving element. Okay. There should be some sort of a gap between these two, but the gap should not be such that it should allow lot of steam leakage. So, that is why there are glands. So, there are different designs of glands. One can go for details of it, but it can be something like this. That means, there are elements like this, number of elements like this, let us say, let us project it. So, that means, if this steam, let us say this is the inside of the turbine, here this steam is at a high pressure, and this is the outside where the pressure is almost atmospheric pressure. So, between this point to this point, obviously there is a pressure difference, but if this steam has to flow, then it has to flow through this zigzag passages, this zigzag passage, and obviously as there is a large pressure drop, the leakage will be minimized due to this particular design. So, this is known as gland or gland sealing. There are other type of designs also. So, whatever we may do for the design, obviously there will be certain amount of pressure drop due to this gland leakage, and that loss will be there. Okay. So, that is the gland loss. Then we will have residual velocity loss. What is that? That we know at the last stage this steam is coming out with some velocity. It cannot come out with 0 velocity, it has to come with some amount of velocity. If it is coming out with some amount of velocity, it is carrying certain amount of kinetic energy, and that we cannot recover. So, that is the residual velocity loss. Then we have got carryover loss. That means, steam has to go from one stage to another stage, and during that time there will be certain amount of loss, and that is known as the carryover loss. So, these are the different type of losses which we will have in a steam turbine, and that is why what is done in between, what we can do, that we can have different stages of steam turbine, and in between these stages we can have different stages of reheat also. Maximum 2 reheat is used. So, we can have, there are some losses. To take care of these losses, the steam will be taken back to the boiler itself, and it will be again heated. The pressure will be low, but the temperature will be high enough, so that it has got higher enthalpy, and then it will be passed to the later stages of turbine, where those are also known as LP stages, low pressure stages. So, where again expansion of high enthalpy steam will take place. So, that is all what we like to say about steam turbine, and I think we will start now the steam generator. As some time is there, let us make a small start regarding steam generator. Well, as you people are from a particular field of trade, we do not have to discuss very elaborately regarding steam generator. Our discussion will be based on marine type of boiler, and but before that, let me today give little bit of introduction to steam generator. Now, steam generator is the device where utilizing thermal energy we generate steam for our further use safely, effectively and economically, so that we can get the steam at required pressure and temperature. So, these are important. Economy is important, safety is important, and obviously in certain application the compactness of the steam generator, that is also important. Compactness means both compactness in terms of volume and in terms of weight. So, particularly for moving systems, so weight is a consideration and also volume is a consideration. And the thermal energy what is used for generating steam from liquid water, that can be obtained from different sources. That can be obtained from fossil fuel, different type of fossil fuel like coal, like oil, etc., and that can be obtained from nuclear source even. For some industrial use where steam is directly used, that means it is not used for power production, but it is used for some sort of process requirement. So, one can use electrical energy also to produce steam. Okay. So, that is how one can have a classification of steam generator or boiler depending on the source of energy which is used for the generation of steam. That means, you can have fossil fuel, you can have nuclear, you can have electric, and among fossil fuel again you can have coal and you can have oil, or you can have a fuel mixture of a fuel, two different type of fuel that can be burnt to have the steam generated. Again, there are boilers, even in marine system this type of boilers are there, where waste heat is used for generation of steam. So, those are known as waste heat boiler or recovery boiler. Then, depending on the type of arrangement of the tubes, we can have fire tube boiler and water tube boiler. There are other classification which I will take in our next class. Thank you.